G'day everybody and welcome to the AI show today. I'm Justin and I'm delighted to have Yaniv with us today. How are you?
Not too bad, thank you. Glad to be here.
A couple of weeks ago you jumped on our previous AI show call where Asa Cox was on, and I thought it would be super interesting to find out more about the work that you've been doing, especially with Molemap and Kahu, and talk us through how some of the AI technology that you've been developing there has grown, and some of the interesting things that you're seeing along the way. So perhaps if you'd like to give us a little bit of an introduction in terms of who you are and what you have been working on, would be fantastic.
Yeah, absolutely. And if I may, I would like the discussion to have a little bit of a technical flavor. I'm not going to go into architectures or mathematical equations or anything of this sort, but I am kind of interested in the technical implications that some of these technologies have and how they affect decision makers and managers in particular, and what kind of things will be interesting to be aware of when you're managing an AI-based product kind of thing. So if I'll use technical terms, that's the reason, and by any means, stop me if you have any questions. I'll be happy to discuss further. So maybe a little bit about myself first. I graduated my PhD from the University of Queensland, but originally I'm from Israel, so I pretty much grew up in Israel and the Israel startup industry. So I'm very much a startup person, even though here and there I worked for big organizations like IBM and the University of Queensland as well. And my main interest, you can say, is AI, computer vision, image processing, machine learning, etc. And that's the kind of startups I tend to work with. I have some background in medical imaging as well, both from the university and from the industry, and currently work with Molemap, which is a skin cancer diagnostic service company. So for those of you who are not familiar with Molemap, Molemap has about over 50 clinics around Australia and New Zealand. And in these clinics, when you get in, you get all the moles on your skin pretty much imaged. Every mole that is even remotely suspicious get imaged with a special dermoscopic camera. And these images, there are three types of images. We have a macro image, which is a kind of a close proximity image that give a good magnification of the lesion. And there are two types of micro images, which is almost zero distance, that the lens is almost touching the lesion. And in fact, there is a glass that actually presses the lesion and make it flat, so everything will be in focus. And we have two types of micro images, polarized and non-polarized. And these are kind of a standard practice in lesion imaging. So you get all your lesions imaged this way, and then all the images are sent to a teledermatologist that then diagnose them one by one. And if there's anything suspicious, you get the results. And in case there's something that's worth going to histopathology or to excision, you get the result. Molemap is around for probably almost 20 years now, and you can imagine with dozens of clinics around Australia and New Zealand, imaging moles every day and getting the diagnostic results, we have a huge database of labeled images. I probably will be, probably don't have to be cautious saying one of the biggest databases in the world for lesion images.
Molemap and IBM have had a relationship for a long time, right? Yeah. Was there any app where people could take a photo and have it processed within?
We have thought about this direction, and what this means is to develop a kind of a camera insensitive or a camera invariant AI type application. However, there are a lot of mole databases out there that are labeled. One of the famous ones is ISIC, a 2019 database, which include many tens of thousands or hundreds of thousands of lesion images. And the performance of AI algorithms, generally speaking, on this database is not great. And one of the reasons that our AI is doing so great is because the image acquisition process is consistent. And when I say consistent, it's always acquired by a camera that have high quality images, that is dedicated to this type of imaging, and usually also done by a clinician that knows how to acquire these type of images. So that's one of our strengths. And there's another point, when you let the user, the patient, acquire their own images, you're exposing yourself to a risk where if the image is not acquired correctly and you get the wrong result, you're actually you may actually mislead the patient, or take the image and send them to the AI and then discover that they are of low quality. Then you're wasting the turnover of diagnosing these images.
So the image quality has it plays a big part in making sure that you are training the AI systems correctly and being able to have a good diagnosis at the end of it.
Absolutely. So the image quality and the labeling quality is the main strength of Molemap. And like you mentioned, we had a collaboration with IBM that then later on turned into a collaboration with Monash University. The researcher that worked for IBM just shifted to Monash University, and the collaboration continued. And Monash kind of developed the first version of the AI that we're using today, or the core architecture, and the quality that this model exhibited was fantastic. And then we started to test it on other databases as well. But then when you operate on different images, even though your training database is good, you may provide it to the AI, even by the clinicians, because one of our target markets, or I should say probably our main market at the moment, is GPs, and GPs are, generally speaking, not trained in acquiring lesion images. So you can imagine that some of these images come back blurry or not exactly focused, etc. So we have to take the AI and wrap it with additional AI algorithms that will tell the user, oh, your image is too blurry, or the lesion is not properly centered, or there's too much hair in the image, or whatever, So the core AI by itself is not sufficient, because you don't want to feed the AI something that you don't know how it will interact with. And that, by the way, leads to another big topic called uncertainty in AI that I'm very keen on at the moment, especially in the context of medical AI.
What's been the transition from Molemap into Kahu, and how's that technology kind of evolved over the last couple of years?
Yeah, so the transition was completely business driven. The idea was to take the technology. So Molemap is a services company, and as a services company, you have a certain operation procedures that are not suitable for a tech startup per se. There has been a decision taken by the investors to make sure that the a Kahu entity go in the right path to raise additional venture capital funds and kind of enclose the equity of this company in the right format. So that becomes pretty much an independent spin-off of Molemap.
That creates the business setting for you to take that technology and start looking at what other ways to leverage and commercialize the imaging and some of the AI processes you've developed?
To be honest, at the moment, we are very laser focused on skin lesions, and the reason is that we want to get the product out there to the market. We have a good technology. We trust the technology. We know it's better than the competition, at least the competition we know about. But the competition is quite fierce, and we know that there are a few companies out there that are going to release a similar product. So we need to be very agile. So that's the main thing. In terms of the technology, 50% of the power of this technology comes from data. And like AI in general, data is at least half of the strength of the technology. The other half comes from the architecture and the way you build your models and you train them and the way you tune them, etc. So the art behind the AI. So you have to have both in order to have a strong model. And the model itself and the expertise behind building the model, yes, we have that, and we can potentially apply to different different fields, and we already have a few in mind that are reasonably close to what we do. But these ones are currently on the back burner until we penetrate the market.
When you look at that architecture and compute power and AI technology develops, how is that enabling you to improve the models and I guess scale up?
Lucky for us, we have this partnership with Molemap, which is kind of a sister company to Kahu, that allow us to get this, an ongoing stream of new data coming in. And this new data is very important, both because it will allow us to continuously improving the model and train it on new data as it comes in. But also because we are aiming at actually developing a new camera, a dermoscopic camera, that will be tailored specifically for this application. So acquiring these images without interfering too much with the clinician's workflow. Because at the moment, what is done at Molemap is the melanographers. These are the nurses that are trained to look and acquire lesion images. They are using a camera that is quite big and bulky and very tailored for the purpose of acquiring lesion images. But if you think about a GP, these guys, they maybe see 5 lesions a day. They don't see 500 like the melanographers. So when they see one of these lesions, on one hand, they will be very keen to know the diagnosis behind these lesion, and they usually don't have the expertise to give accurate diagnosis. So when they have doubts, and they have quite a lot of them, they either excise and send it to histopathology or send it directly to the dermatologist to diagnose. So imagine that this GP will have this small camera on their desk where they can just grab it, take an image, and within seconds or minutes, in the worst case, get the diagnostic results on the screen. It's like a digital histopathology, if you like. So having this data streaming is also allowing us to train the algorithm on the new images on the new camera, but also kind of adapt to different populations and different lesion types. And you can imagine that even if we go to different countries, for instance, our main market, the main target market at the moment is the US, as you can imagine. The skin types even that you see in the US are different to the skin types you see in New Zealand or Australia. And you have to make sure that your algorithm is robust enough to cope with these skin types, etc. So this is one of the challenges we have, making sure that we cover enough variety of conditions and skin types and even patient conditions that sometimes you think will not affect your algorithm. Pregnant women, for instance, have slightly different mole appearance than the average person. Kids have a slightly different mole appearance. All these things, may affect your training set, and you would like to acquire all these images and enforce your data.
All the different variables that come through the data sets, not just the quality of the image, is it? But yeah, it's interesting, different, how all those elements, are competing with you to get, quality results back.
It is, and one of the probably interesting topics that I'm currently interested in, and actually we are working on this with Monash as well, is the uncertainty in AI, generally speaking, and medical AI in particular. So this problem comes into place, especially in these situations when you have a database that you train on, but you know that some conditions or classes of your AI, you should say, have very rare instances or very infrequent in your training set. And sometimes you don't even have any samples of these occasions. So what happens when you now apply your AI to one of these conditions outside your training set in the clinic, for instance? The AI is, by the way it's trained, and those of you familiar with the softmax layer and these properties of how the AI is trained, is intrinsically forced to give an answer based on the classes it was trained on. Nonetheless, it cannot say everything is 0. It has to assign a score to every class in a way that they will sum up to 1. So what usually happens in these cases, let's say you train your AI on 200 lesion types, and now you introduce something completely different, then it will just choose the one that looks most like the lesion that you're introducing to it, even if it's quite different. So you may get an answer that is completely wrong just because of this intrinsic property of the AI. And this is something we would like to be able to detect or even assess. So nonetheless, I mean, if you take a trivial case and you say, oh, okay, this AI is trained on on skin lesions, but suddenly I put an image of a dog. Nonetheless, you don't want to get an answer that this dog is a malignant lesion, right? But even in a more complicated case, when you put an image of a pimple, I don't know, something that is definitely not relevant to detect classifying skin lesions, but may confuse the AI more easily because it's skin, because it's something on the skin, etc. So you want to be able to say, oh, okay, here in this case, I'm saying that this is a malignant lesion, but because it's not something that was in my training data set, I will give you some indication that I'm not very certain about the result. So even though I'm presenting this result, you may not trust the AI in this case. And these kind of things become, I think, more and more important in medical AI in particular, because we used to think about a medical AI as explainable when we had these traditional classifiers, the support vector machines and random forest, where we can dive into the inside of a classifier and understand how the decisions are taken and even formulate the equations and make sure that everything is regularized properly, etc., measure the noise in the data. You know, we could do a lot of analytics on these classifiers, and suddenly we move into this black box called deep neural network that does all these fantastic things. And on one hand, we know a lot about these networks, but once they are trained, we have no idea how to come to their decisions. You know, when once you feed an input, you have no idea what is the combination of numbers running in the network that lead to a specific decision. And we don't have a way to explain it. But when you're providing,
how does that work with the EU regulations around explainable AI? And someone, whether it's a physician or a customer, needs to be able to understand how it came to that decision? Or is that just something now that we've got to get past and we've got to trust the accuracy on? Or
that's a fantastic question, and a lot of people thinking about it, especially from regulatory perspective, right? I mean, you want to approve a product and say it's safe. How do you say it's safe if you don't understand how it works, right? So there are probably a couple of different answers to that, and people are tackling these problems from different directions. And at the moment, it seems like the regulators and the community in general will have to accept the fact that you cannot well explain the way the classifier get to the decision. And this means that you will need to validate the performance of your classifier very thoroughly and kind of show beyond a reasonable doubt that it's robust and can operate on unseen population in a safe way. There is the whole concept of explainability and interpretability of classifiers. Interpretability usually usually people tend to join these two together and use the word explainability. But when people say in the literature interpretability, usually they mean explaining the mathematics and the variables behind the classifier and how it gets to analytically, how it gets to the decision. While explainability is more of a high level slash intuitive explanation of why the classifier operates the way it operates. So to solve the explainability problem, sometimes what people do, they say, okay, I'll take some elements from the network that I can explain. In a convolutional neural network, for instance, it's the filters that sometimes show you some shapes that the network managed to detect. And I'll say, okay, if I detect these shapes and these places in the image, I can explain why the network came to this conclusion. I think we will have to move towards better and more systematic testing of AI because it's getting harder and harder to explain how it operates.
John, you had a really good question. Does that kind of answer?
Justin, I think it's something different. It's just about the whole process. And I don't know anything about image processing, but I sort of understand that you can put a human in the loop either before and then have the machine learn basically after you've labeled it, or maybe the machine has a go and then the human says, no, this was the right answer. So you sort of got that training data set. But I'm just wondering, having trained this new camera with its AI, you talked about quite a tight time frame. Will that be just automating a process where the AI does the read and actually makes a diagnostic decision and sends it back, or sorry, suggests something to the doctor to make a decision, the GP, or is it going to go through a human in the back office somewhere? In what way does the AI support that workflow of this new camera where you can sort of, in a GP practice, take an image and then something happens magically? Just sort of curious about how the human fits in there.
Yeah. So what happens, the first thing we are going to do is as part of the regulatory process is clinical trials. And part of the clinical trials will force us pretty much to have a dermatologist in the background that kind of gets all the images, diagnose them, compare them to the AI and say, okay, here the AI was wrong, here it was right, etc. Mm-hmm. So this will be the first stage. We have to go through this stage in order to validate the robustness of the algorithm in a clinical settings. Because at the moment we do have brilliant results, but they are only tested on our test data set, images that were acquired at Molemap clinics. Maybe at the GP clinics, the images will look different and maybe the AI will behave differently at the end of the GP. So that will be the first stage. Once we went through all these stages of clinical trials and we are confident that the AI is reliable, and when I say reliable, is as reliable as a dermatologist, because we know that the accuracy of dermatologists is not 100%. Right. We kind of have some idea what it is, the range, and we are aiming to be at least as good. Once we can claim that reasonably confidently, then we say we trust the camera to pretty much give you the final result, with the acknowledgement that it will not be always right, but it will be more right than most human observers.
Brilliant.
Expert observers, I should say.
Excellent. So it becomes a medical device that's autonomous. It drives itself off its own AI and the data that's gathered, and so
that's the aim. Yeah,
fantastic.
That's the aim.
Awesome. Well, thanks for that.
Another challenge in medical imaging, AI in general, and skin lesions in particular, is the accuracy of the labels. So we have a huge database, but the labels are coming from dermatologists looking on the images, making their diagnosis, and we use this as ground truth, but we know that dermatologists make mistakes as well. Nonetheless, the ones that they think are malignant are sent to histopathology, which is more accurate than the dermatologist, but still not 100% accurate. So as funny as it is, or not funny, it depends how you look at it, if you put some random person to judge whether an image is a dog or a cat, they'll usually be much more accurate than a dermatologist, expert clinician looking on a lesion and say whether it's malignant or benign or what type of malignancy. So this is a challenge we have to face, and knowing that the labels are not accurate and will never be completely accurate, we are still aiming to be as good as the dermatologist, using tricks and techniques that give us the opportunity to develop this robust AI, let's say.
So what sort of accuracy do you need to be able to get to before you establish that customer trust? Obviously, getting it into the doctors with the new cameras vastly increases the number of scans that you're getting and the number of labels you've got. So hopefully, I guess that's there to try and increase the accuracy model and build that up. But is there some kind of, is there a threshold where you've got to get to before you can really deploy this as a customer facing?
So when you say customer trust, there are two aspects to it. One is indeed the accuracy. And when I say accuracy, it's accuracy in the broad sense, because accuracy by itself as a technical term is not the best measure of diagnostic performance of a classifier. So you have all these terms like specificity, sensitivity, positive predictive value, negative predictive value, a collection of different measures that tell you essentially how the classifier performs in different ways. How many malignancies you miss, how many benigns you think are malignant, from the ones that you say are malignant, how many are really malignant, et cetera, all these measures. And you can tune your classifier based on your receiver operating characteristic curve to be as sensitive or specific as you want. Now, there are no specific thresholds that you need to cross in order to say my classifier is good enough. However, there are two ways to gain the customer, which is the clinician trust. One of them, you need to show that, at least according to literature surveys of a clinician's accuracy and consistency, you perform at least as good as a clinician. Usually, the customers and humans in general will be less forgiving towards AI than they are towards human mistakes. And you can see that in autonomous cars, that per mile make much less accidents than human drivers. Still, when they have one accident, you hear about it on the news. Why? Because you're much more suspicious or cautious towards AI. It's a psychological thing that we will, as humans, will need to cross at some stage and say that's 10 times more safe. We'll have to trust it, So you have to be better than human, generally speaking, in order to get trust. And you have to show that according to literature, you are better than a human or expert observer. The second thing is back to the explainability topic. When you just give them a black box and you say, trust me, it works, usually they will not trust you. That's understandable. So you have to, at least to some degree, even if relatively shallow, but still say, look, it works because he takes this decision and that leads to this decision, and we have these layers of a diagnosis inside the mechanism of the AI, and then we give them different levels of diagnosis, like we give them the malignant benign, and maybe under that, what is the lesion type we think it is, and maybe we go further with more details, and obviously the more details you expose, the less accurate you are with the details. So you have to balance between give an accurate result and provide enough details for the customers to trust your product.
Matt, Siku, any questions?
How much work is going on in sort of open source for this kind of stuff? I mean, who's the competitor, I suppose, for the work that you do? Not perhaps commercial, but what are the challenges around open source?
So first of all, there are publicly available databases. If you're talking specifically about skin lesions, there's the ISIC 2019 lesion database. That's publicly available on the internet. You can train and test on it. It's quite big, and it's a database of lesions taken from with different cameras, different clinics. In terms of the architecture to diagnose these lesions, if you think about the easiest way to do it, you can take pretty much any CNN and say, I will just train it on this database, and you'll get some reasonable results. Not good enough maybe for clinical applications, but you will see that there is enough information in the images to make reasonably accurate diagnosis. So that's really what you're looking for in the first instance, right? You want to know that the information is there, because otherwise there's no hope. But then if you look into starting tailoring the architecture specifically to your application and your type of images, that's where the art/challenge starts, right? So nowadays, you get, I think one of the reasons why it's so hard to find a good AI engineers is because every software engineer that knows how to download and run a CNN on a bunch of data call themselves AI engineers. And then you discover that with the slightest problem, when the data doesn't fit or the architecture is not the best one for the data, they have no idea what to do. They just say that's the results we can get. Where in fact, there's a lot more you can do if you know how to do it. So, but if you're looking for the very simple case, any CNN pretty much will do the job on this kind of database.
That is great, Yaniv. Thank you for that. That was my first question. I'm Seku. I'm calling from Christchurch, actually. And I work in a kind of a lab, JIX innovation lab, which we work with the CNN and image recognition for a couple of things, actually. So I have a couple of questions. You already answered my first one because I was wondering about your ML models, like, where do you get it? Like, is it open source? Because most of the times we are developing a classifier for waste as such. So it's like, we don't have anything. So we have to use a synthetic data for it. So we don't have much data that is available as such. So that you have answered that first question. The second question that I had was in terms of the models that you've obtained from these open source, like, what kind of disparity do you have in terms of, or should I put it in terms of the racial disparity? Because the skin lesions for me kind of has different kind of layers to it in terms of identifying, okay, this color goes to that, this color means that. Like, I'm not sure about the medical set of things. I'm just working in the technology set of things. But what is the kind of balance or like outcome, like, that you get that is pretty good in terms of the input that you feed into that? Or should I paraphrase that question? Is it too?
Yeah. Okay, so I'm not sure I got the second one, but let me maybe answer the first one first, and then so I guess the first one is asking what kind of architectures or technologies to use when you don't have a lot of data, or where you have a
yeah, exactly. Yeah.
So I think the question there is well, how much data do you have relative to the problem you're trying to solve and the performance you're trying to achieve, and then how does this data look like? And when I ask these questions, I mean, there is a tendency these days to pretty much throw deep learning at anything you get. Right, and people tend to forget two things. One, sometimes you don't have enough data for deep learning. Deep learning usually requires a lot of data, although as the architectures improve, they're becoming more and more insensitive to the amount of training data you have. But we are still far away from being able to create a relatively accurate model with very little data with a deep neural network, especially if your data is different to natural images or images that the network was pre-trained on. So in these cases, if you can, for instance, extract specific features, or you have expert knowledge that say, for instance, let's say you're trying to detect, I don't know, circular objects on a conveyor belt, then you have the prior knowledge that this is a circular object. Then there's no point training a neural network, right? Because you can just use image processing / computer vision techniques to detect circles, right? So that's kind of an extreme example, but in many cases, you have a bunch of features that you as an expert in the field will very accurately tell you whether this is what you're looking for or not. And even different combinations of the features may be a good enough cue to tell you if that's the object you're looking for. Then there's probably much more merit in training a classic classifier that can be very accurate on very little data, rather than throwing all the images into a deep learning network, and then discovering that 200 images is just not enough for a deep network.
Yeah, because it needs a humongous amount of data and, like, things to feed into, and you don't have anything, like, that seems to be the major problem every time we're going into something. You're like, you don't have the data sets to do that, and CNN needs like humongous volumes of data to be able to make sense or get an outcome, actually. And that was one of the reasons. And the second one was actually, let me rephrase that again, in terms of the diagnostic algorithms that we are talking about works to create a, has a new source of racial disparity in patient care, in terms of the data sets inserted. So how do you kind of intervene and say, okay, great, this is a really good, I'm still not able to put into words, but how do you kind of say the outcome is not biased, or is has its equal amount of black skin or brown skin, or because I'm not sure how the open source for your industry works. Is it kind of equivocal in terms of the skin tones and colors?
Okay, yeah, I think I understand what you're asking. So first of all, just to clarify something, there's no open source in our product in any way, and we are not producing open source code. We are using, I just heard the words. I wasn't sure if that's clear, but yeah, in terms of bias to performance, that's a really good question, to be honest, and that's a question that comes up quite a lot in the context of AI, especially when you deal with people, right? Because the data that you use to train the algorithm may actually create bias, intrinsic bias in the AI outcome. And for instance, skin types. Look, there is no good answer to that. And the problem is that in our case, for instance, we have in a skin, in dermatology, you categorize skins from 1 to 6. Well, 1 is the brightest / pinkish, and 6 is the darkest. And the thing is that with skin types 4, 5, especially 5 and 6, skin cancer is very, very rare. So it's very hard to get training data on these skin types. So this creates this situation when on one hand, these people are lucky because they are less prone to this problem, but on the other hand, it gives you less data to work with and provide good product for these kind of skin types. So we have to go through all the hoops of acquiring this data from any source we can in order to, for the very least, show that our product is robust enough to operate safely on these skin types. And the regulator requires that.
So do you consult with the doctors every time, it has a report, you consult with the doctor saying that, hey, this was your analysis of these particular patients, and this was our algorithms analysis, and is that how you make kind of bring trust into to the practitioners?
You mean in terms of enriching the training data set?
No, in terms of how do you kind of get the trust from the practitioners? If you want to show that your algorithm, that your models work, how do you convince them, saying that, okay, great, do you, I mean, I'm hoping you do the analysis of 10 or 20 or 100 different patients' data, and then you do the manual analysis and we compare each other. Is that how you kind of do it?
So that's a long process of validating the performance of the product first in-house on a test data set that we have, that is tens of thousands of images, just the test, and a significant portion of that is actually dark skin types. So obviously much smaller than the other skin types, but still enough to make this, to do the statistics. Then you go to clinical trials. So clinical trials will evaluate the performance of the product in the clinics, in the clinical setting. So to make sure that our test set is not biased itself, right? So you want to make sure that when the camera is held by the clinician that is supposed to use it, the images are still robust enough, the performance of the AI is robust enough, and everything performs the way you expect it from your original test set. And only once you go through all the hurdles of clinical trials, then only then you can get regulated and get your FDA approval.
Thank you for your time, Yaniv.
My pleasure.
I love the answers that you gave for everyone else.
Look, great questions, and really interesting conversation as well. Much appreciated.
My pleasure. Thanks for having me.
No worries. Thank you very much, and thanks, John, as well for joining us. Yeah, really interesting discussion, and just really interesting to understand some of the complexities with building that data set and that technology. So huge kudos, and yeah, really appreciate your time. Thanks for joining us on the AI show.
Great.
Cheers.
Thanks very
Cheers,
much.
guys. Thanks very much.
Thank you, guys.
Bye.
Thank you, Justin.